Kia ora tātou. In this video we'll go over the 2017 exam question 2 part A, which has got a couple of questions on weak bases and buffer systems, so it's a good introduction to how to do these calculations. So the first question, ammonia is a weak base, and we've got the pKa and the Ka there. Calculate the pH of a 0.105 mole per litre NH3 solution. So there's two ways to do this. I'm going to label them the long way with no memorization of equations, and the short way. So we'll go through both of these ways. I'll do the short way first, and then if you're comfortable with the short way, then you can just skip here to the next question. Otherwise you can have a look at the long way, just in case you forget. There's a formula that you need to remember if you're doing this the short way. So the formula that we use when we're doing this the short way, and to derive this is quite tricky, and I'm not able to do it, so I can post something to show how to do that from another website or from another book. But we use this formula, which is H3O plus, concentration of hydronium is equal to the square root of Ka times Kw divided by the concentration of the base, so in this case NH3. So we just need to put the values in that are given to us. So we've got Ka is given to us here, Kw we need to remember is 1 times 10 to the power of negative 14, and then we're given the NH3 concentration there. So if we put that into our calculator, I'll just do that quickly now, then we get 7.40 times 10 to the power of negative 12. And because the answer is asking you to calculate the pH and not just the concentration of hydronium, we then just need to take the negative log of that answer, and that will equal negative log 11.1. So that's pretty quick and easy, but the only thing is that you need to memorize this equation. This is not given to you in the resource booklet. So the other way that we can do it the long way, and skip this if you're happy with memorizing that equation, is that we would write out the base dissociation expression for ammonia. So ammonia will react with water, H2O, to form NH4 plus OH minus. So we would go Kb equals the concentration of the products, NH4 plus OH minus, divided by the concentration of the reactants, and so we don't include water because that's a liquid. And then what we can do is we assume that NH4 is equal to OH minus. And that is because, we assume that we're starting off at a pH of 7, so there's no hydroxide ions that are coming from any other source. So any ammonia molecule that dissociates will form in equal portions NH4 and OH minus. So we can make that assumption. And then we need to redo this formula so that we've got Kb equals OH minus squared, so we can do that making this assumption, divided by the concentration of NH3, and then we can go Kb times NH3. If we take the square root of that, then we get the concentration of OH minus. But the thing is that in the question, we're not given Kb. We're just given Ka. So we need to convert Ka into Kb, and I'm running out of room already, so we can use the formula Kw equals Ka times Kb. So Kb equals Kw divided by Ka. So we'll insert this. Instead of the Kb, we'll put Kw over Ka because we have those values. So OH minus is now going to equal, I'll get us some more room. You can see why this is a long way. and I guess there is still some memorization required. So that equals the square root of kW divided by Ka times NH3. So what we get there, I'll just put this in the calculator. So that one equals 1.35. This is my first video done while at school, by the way, so you might be able to hear some people outside bouncing balls and things. 1.35 times 10 to the power of negative 3, and then we need to convert that to the concentration of hydronium ions. So to do that we use the formula Kw equals H3O plus OH minus, and then we go H3O plus is equal to Kw divided by OH minus, so I'm going to go 1 times 10 to the power of negative 14 divided by this value here, so H3O plus equals 7.40 times 10 to the power of negative 12, and then we go negative log of that answer, so the pH equals 11.1. So you can see there, this is quite a lot longer compared to this, which was 2 lines. But that's the way that we're given all the equations. Otherwise, you just need to memorize this. Okay, so yeah, having gone through that, you might see the motivation for memorizing this equation. Okay, we'll go on to the next question that has a long way and a short way as well. So dilute hydrochloric acid is added to the NH3 solution until a ratio of NH3 to NH4 plus in the solution is 5:1. Determine the pH of the solution and evaluate its ability to resist a change in pH when small volumes of strong acid or base are added. So to do this one, we'll do the long and short way. So I'll do the short way first again. So the short way is to use the Henderson-Hasselbalch equation. So that is pH equals pKa plus log, and then we go the concentration of the base divided by the concentration of the acid. This one is easier to derive, so if you if you don't memorize it, then you can actually work it out in the exam, but perhaps the best way is to just memorize it. So pKa plus log base over acid. So just remembering that the base goes on top of the acid. Think of your own way of memorizing that as the most important part. And then we can just very easily put this into an equation. So pKa is 9.24. So we'll go pH equals 9.24 plus log base over the acid. So we've got NH3 and NH4. So NH3 is the base, NH4 is the acid, so NH3 is 5 divided by 1. So we don't have the specific concentrations, but because this is just a ratio anyway, we don't need the units. And then that's going to equal, just quickly put this in, 9.24 plus log 5. So we get 9.94 is the pH. And so that makes sense because we've got more base than acid, so if we've got more base, then we would expect a higher pH than the pKa, which is what we would expect if we had equal concentrations of base and acid. Okay, so that's the quick way. You can stop the video there if you're happy with that. The long way of doing it is that we would need to write out the equation of NH4 dissociating in water. So NH4 plus H2O. Excuse me for not including states, just trying to go a bit faster. NH3 plus H3O plus. So the acid dissociation expression that we would get is NH3 H3O plus divided by NH4 plus. And so we can then go H3O plus equals, and I'll times both sides by NH4 plus, and we've got the Ka there already, divided by, we'll divide both sides by NH3. So in this one, we are then going to use the Ka value, which was 5.75 times 10 to the power of negative 10. So we go 5.75 times 10 to the power of negative 10 times the acid ratio, which is 1, divided by 5, which was the base. Remember that from last time. And then we equal 5.75 10 1.15 times 10 to the power of negative 10, and then we go negative log of the answer to get the pH, and we've got it 9.94. So the same answer, but just takes a little bit more a little bit more work. Okay, so I'll just finish off by showing you how to derive the Henderson-Hasselbalch equation. So we'll use this formula here that we were able to get from our acid dissociation constant. So H3O plus equals Ka times NH4 plus divided by NH3. And then we take the negative log of both sides. So negative log, negative log, negative log. And so the negative log of H3O plus is just the pH. The negative log of Ka is the pKa. And the negative log, well, there's no shortening for that. So we get negative log of the acid. So I'm going to substitute acid instead of NH4 plus, divided by the base. And then you'll remember that when we actually get the equation, it should be base over acid. So what we can do is change that sign to go pKa plus log, and then if we change the sign to a plus, then we can just switch those around, or we need to switch those around. So we get the base divided by the acid. So I hope that helps with your buffer solution. I'll try and get some more videos up as quick as I can. Thanks for watching. See you next time.